Greetings, everyone. We're back, and we're going to talk a little bit more about statistics here. So, let's move on forward with this stuff. And well, anyway, I keep hemming and hawing here, as you'll find out I do all the time. But no, the reason I'm hemming and hawing is that this is more descriptive statistics. By this point, you probably have gone through this on Khan Academy. If you haven't yet, you will. So I'm going to move a little bit quick, and we've got some things to talk about, and I've got some examples, and we'll look at those examples and show you how I like to get to know the data, so to speak, and a small, quick exercise that I find useful to helping understand statistics. At least it was useful for me, especially along the lines of descriptive stats. So the first thing we have to worry about is this concept of dispersion, right? In other words, variability. So think of a data set with 25 people in it, and I don't care what you're measuring, ages, IQ scores, whatever. And we're going to do our mean, median, mode on that, right? So our really simple statistics. And then after we do that, we need to know how accurately does each one of those things represent the data set, right? So, because not all scores are exactly the same. So let's say we get a mean, let's think of number of children per family in the United States, 2.54 or whatever the old statistic is. I don't know what it is today, but that's kind of the joke, right? So how well does that 2.54 represent the people? Well, it doesn't represent any one person, but it might represent the sample overall pretty well. So how many people fall at or around 2.54? Was there a bunch at 3, a bunch at 2, and none at 17? You get the idea. So we want to see how accurate that mean is. And we're going to look at that, and we're going to come up with some statistics today to help us understand how accurate that is. In other words, we're going to understand the value of the mean, because the mean is really what we're going to be focusing on primarily in this course. We'll do a little bit with the non-parametric statistics, and I'll have a little lecture about non-parametrics, but nothing serious. But ultimately, for the most part in psychology, we like to use the mean. The part of the problem there is it's not always appropriate to do that. And we'll get to that later on in the quarter. So, again, once we look at the dispersion of our data, in other words, when we get a histogram, when we plot that stuff, then we can start to choose the appropriate statistic. All right, so let's look at the basic stuff here. The most simple measure is the range. Lowest to highest, right? So subtract the highest from the lowest, or lowest from the highest, however you say that, and the lowest from the highest. I always get confused. Anyway, so subtract the lowest from the highest, and then that'll give you your range. That is great, but it doesn't tell you squat. It just tells you where that low end and the high end is. It doesn't tell you how many people are at the top end, how many people are at the low end, where they're lumping at in the middle. It doesn't tell you anything. It just tells you that. Something else you'll see quite frequently, especially in our field, is the interquartiles, right? So the middle 50% of the data. Right? So this is based on the mean or the median stuff. So you take the median, find that, and then take the median, the halfway point between the lowest data point and the median, right? And then take the halfway point between the median and the highest data point. So you find a median between the medians. Kind of weird sort of thing. A median of a median after a median. Anyway, you get the idea. So then ultimately those 2 points that are halfway between the median and the high end and the halfway between the median and the low end, those 2 points are going to make up your interquartile range. Right? That shows you, it tells you a bit about the dispersion, right? It tells you a little bit about that variability that exists in your data. But we can get a lot more complex than these things. And those are useful, but so that's it. I mean, it just describes the data. And I like to get to know the data a little bit closer than that. And one of the things that allows you to do that is to focus on variation itself. Right? And ultimately, we're going to calculate the variance and the sum of the squares and all those things here. So let's look at this stuff first. So let's get some variability in our data. Don't worry about that second data point yet. I wanted to get the graph up. Right? So each green dot represents a data point. The big, bold black line there represents the mean, so x bar, right? So there's our mean. So what we have here is a bunch of data, and you'll notice that only one data point falls on the mean itself. So what we have is those red lines, right? So let's look at the red lines here. So those red lines represent residual. Okay, so in a sense, when we talk about regression, we talk about them as residuals. When we talk about other things, we're going to talk about them as deviations. In other words, this distance from this green dot to that mean is how far that data point deviates from the mean. And again, this one deviates from the mean by that far, and this one deviates by that far, and so on and so forth. Ultimately, we're going to play around with these deviations to come up with a measure of how accurate this is. Right? So you might think right off the bat, wait a minute here. couldn't we get an average deviation? So if this one deviated this much, this one deviated this much, this one deviated, you could add all those things up, divide by the number present, and you get an average deviation. Well, yeah, you'd be right, okay? But it doesn't quite work out as simple as that. But ultimately, that's what we're going to do. We just have to tweak our data just a little bit, right? Just a little bit to make that function. And we'll see why you have to tweak the data to make that function here in a minute. Right? So ultimately, what we're going to go for, before we get to that dividing by, right, and getting that average deviation, we need to sum all of these things, right? So the sum of the squared deviations from the mean is what we're going to play with here. Okay? And here in a second, we'll get into some actual data. So I know that this is a little bit of a weird concept at the moment, but we'll look at that actual data and you'll see why. So keep in mind, we're going to sum up, right? Because we're trying to get ultimately we're going to get an average, right? We're going to get a mean of the deviations of each data point from the mean. And that will tell us how accurate our mean is with regard to all of our data. Okay? So we're going to, in order to get an average, we need to add everything up, and then we need to divide by a certain number. And that certain number is going to be n or n minus 1, and we'll talk about that in a second. So when we add these things up, right? So we're going to sum these deviations, and what you'll notice is that we can't just sum the deviations themselves, and because it will always be 0, and you'll see why when we get to the data set. So we have to square that. We have to sum the squared deviation from the mean, right? So we're going to get the SS, which is the sum of the squared deviations from the mean. So let's go back to our data set and let's look at how we get to the sum of the squared deviations from the mean. So bear with me here as I switch over. Ba-bong! There's our data. All right, so let's dig into this a little bit further. I'm gonna maybe kind of zoom in a little more. 175. Ah, there we go. All right, nice and pretty. Okay, so I've got ages. I just made this up, here a few minutes ago. So this is not real data, but it gets you the idea, right? The first thing we're gonna do is get all of our x's. Those are our raw data points. Okay. Whoa, sorry about that. Those are our raw data points. Those are right there. So we got 21. We could come up with a range. So the lowest score is 18. The highest, what do we have here in terms of ages, is 31. Okay, so we could just subtract those things and we could get that difference and find out what the range is. And that's all well and good, but it doesn't tell us very much about our data. Okay? Our sample size, or n, notice that's lowercase n because we're talking about sample size, not a population size, is 25. So there's 25 data points in there. So we need to calculate the mean first. So we did that, or I did that, and we have 23.56. Right? So in Excel, it's really easy to do. If you look up top here, here's how you calculate the mean in Excel. Right? So right up there. Equals average, parenthesis, A3, colon, A27. Notice that all that stuff is highlighted, so we have our average. And it gives us 23.56. So then I created another column called the mean, and I put 23.56 in each one of those. Right? So now what we're going to do is take, oops, sorry about this. My mouse is a little jumpy today. All right. So now we're going to take x, and we're going to subtract the x bar. Right, so x minus the mean equals the deviation. Right, so x minus x bar, or the mean, right, equals your deviation that you have, okay, for that particular data point. So we know that the 21-year-old is minus 2.56 years away from the mean. The 22-year-old is minus 1.56 years away from the mean, and so on and so forth. So we get all those things. Here's why. Remember earlier I said we can't just sum all those things up and divide by the number present. And here's why. Think about what would happen if we took a sum here. If we summed the deviations, which is ultimately what we're going to try and do, but we're not quite there yet. Okay, so if we sum these deviations, and sometimes Microsoft sucks, and it might suck here when we try this, but we'll see if it works. Right? When we sum these deviations, what do you think is going to happen? Think about where the arithmetic average is. Arithmetic average means the arithmetic middle, right? Not the median, but the arithmetic middle. Where is that like half of the values of scores fall above and half of the values of scores fall below. Not actual scores, but the values of those scores will fall above and below. So that halfway point is represented by the mean in that sense, right? The arithmetic sense, it's represented by the mean. So half of your data functionally is going to be below it, and the other half is going to be above. So if we sum all this equals sum, we'll get what you probably expect, which would be functionally 0. Okay, that is 0.0, well, 7.1 to the negative 15th. So you get the idea. It's a little bit off because of rounding in Microsoft, but the basic idea is if you sum that, let me clear this all out here. So if you sum that stuff, then you're going to get 0. And again, if I had this done up a little bit differently, you would see that it's actually 0, but I've been rounding. Normally, in order to make this legible, I don't have it carried out to 4 data points or whatever, so it rounds up and it loses itself a little bit there. So we can do it this way, though. Let me format that cell. And maybe you're learning a little bit about Microsoft here, too, as you go. So let's just do no data, 1 or 0 decimal places. Okay, so now if we sum that, ooh, bear with me. Come on, come back. Equals sum. Now it'll equal 0. There you go. I don't know what that's doing over there. C28, whatever. Okay. So the sum of those is all 0. It's just the way I had Microsoft was setting, the way I had the settings. Right? Now, if you take the average, if you try to get the average of this, then you're going to end up with 0, right? 0 divided by anything is 0. So if we left it right here, we would conclude that our mean perfectly represents every single data point. But we know that's a bunch of hogwash because we can see that there's 21 and 23 and 22 and 23. It doesn't match up. The mean doesn't accurately represent everybody. So we know that the average deviation can't really be 0. And even when we sum those deviations, it can't be 0. So it doesn't make any sense, right? So what we have to do is we have to either convert them into absolute values or square them, right? And it's easier actually to square these, and that's what we have in this column over here. Sum of the squared deviations. Right? So x minus x bar, right, squared. So we've got the squared deviation, so negative 2.56 times negative 2.56 equals 6.5536, right? So we've now done something, though, that I need you guys to focus on. We started out in years. Then we got the distance in years, right here, okay, from the mean to the data point. That's the deviation. But then we took it and we squared it. What in the world is a year squared? Right? We're going to come back to that one in a minute. That's a problem. Right? We eventually have to, we're going to have to take the square roots to get rid of that squaring, because at this point a year squared doesn't mean anything. And one of the things that just drive me insane with statistics is that a lot of times people will convert their data and all of a sudden you don't know what it is you're working with. It's like, okay, well, that's the year of the square of the whatever of the pig. And it's like, what? I don't understand. That doesn't represent the data that I actually took. So make sure you always keep an eye on how that data is and what it represents. And don't think of the number as something other than what the data is actually supposed to measure. So if this is intelligence, think of it as intelligence scores. Don't just think of it as the number 6, right? You got to think of what it represents and making sure that you keep it at that level, so to speak. So right now we're not at that level. We've squared these things. But we had to do that in order to get to our sum of squared deviations from the mean. So here we go. So down here I took the mean, all right, so that's what we have, and the sum of squares, so the sum of the squared deviations from the mean. All I did was sum all those up, just sum that column, 386. Right? So now we know that if we add everything up, we got 386, and as you might expect, we're just going to get an average for that, so we're going to divide that by the number present. So we've got 25. So we're then calculating the variance. The variance is by far the most important statistic in statistics. Almost everything is based on variance. There's 2 kinds of variance, systematic and unsystematic. Look at that, I remembered them this time. Anyway, there's 2 kinds of variance, and they're all basically calculated in the same way. So it is the cornerstone for all of the inferential statistics that we're going to do down the road. So we need to understand that concept of variance. So in the meantime, I'm going to jump back. Actually, yeah, I'm going to jump back over here to my slides. Okay, we already looked at that. All right, so now let's look at how that variance ties in with everything. Right? So the variance that we have, we calculated our variance based on the sample. Sum of squares divided by n. There's another variance that we need to worry about, and it's when we take that variance and apply it to the population level, right? Because we're not always just interested in how our statistics represent our sample. We're really interested in how our statistics represent the population, Right? So if our population is fourth graders, we want to know how accurate is this with regard to fourth graders. So our variance at the population level is sum of squares divided by n minus 1. Now think about why it would be n minus 1 for a second. And for this, we've got to go back to basic math. Right? So sum of squares, which is, remember we're calculating an average here. Okay? So the sum divided by the number of those things that created the sum. So sum of squares divided by n gives us a number. If we take sum of squares divided by a number, or n, okay, let's say n was 25 as it was, and then now we're going to make it 24, what's going to happen to the number? It's going to get bigger, right? So anytime you have the same numerator and a smaller denominator, then the end result, the equals, right, whatever it equals, is going to get larger in comparison. That's an interesting thing to think about. And it's probably one of the weirdest and coolest conventions in statistics, and one that is absolute, complete, 100% total guesswork. Why not n minus 2? Why not n minus 3? Well, I don't know. Some guy named Fisher decided on n minus 1 years ago. And then there's been a lot of statistics to test it and a lot of confirmatory stuff, and it seems to work pretty well. So it's not a complete guess anymore, but it started out as a guess, and there's a bit of guessing in statistics every now and again, but there's always some statistician sitting in an office, kind of like I am now, crunching numbers day in, day out, nonstop, testing the assumptions and the probability that these guesses are accurate and all that stuff. So anyway, nothing to worry about, but the basic idea is that we're making an adjustment to our variance. And remember, the variance is the average deviation from the mean. We're still squared, though, so let's not forget that. So it's that average deviation from the mean. So now we're saying that at the population level, the average deviation from the mean is going to be a little bit bigger. In other words, we're being conservative. We're just saying that, you know what, for our sample, we can calculate exactly what that is, but at the population level, we're not 100% sure. There may be other factors taken into account. In other words, we're saying that we didn't necessarily have a perfect sample. And as you guys have learned from your readings, you're almost never going to get a perfect sample. So we're conservative. We fudge the data a little bit. We go n minus 1. We say this is probably going to be a better representation of the population by reducing our sample size by 1, which then increases our variance. Well, we're not done yet, all right? So that's it for sample and population. So let's move on to standard deviation, which is the next statistic. Oh, don't get overwhelmed. You already know most of it. Remember what we had above the variance, right? So S represents variance. Okay? So that's our population variance. So S is our population variance. So keep in mind now that all we're doing to get the standard deviation is putting the data back to the way we found it. With the variance, we were still squared years. All we have to do now is get rid of that squared years thing. So how do you get rid of a square? You take the square root. So the standard deviation is simply the square root of the variance. All right? So that's all we've done. Just took our sum of squares divided by n minus 1, so at the population level, took the square root, got our standard deviation. That's all there is to it. Right. Now you're going to notice that I actually calculate in the sample set here, the data set here, I actually calculated the standard deviation based on the sample mean, or the sample variance, but that's okay. So, and then we're going to come back to the standard deviation, and you're going to see how important it is here before long. All right. So notice that we've done all of our x minus x bar squared. We got our sum of squares. We divide that by 25 to get the variance. So there's our variance. Now we're going to take the square root of the variance. So we're saying, okay, the way we interpret this is that on average, each data point is 4 years away from the average data point for that sample. So that's our standard deviation. So how far does each data point deviate from the overall mean? And that's all we're doing. And this can be interpreted in years. This is squared years, and we don't know what in the world that is. But this is years, and we understand it. So it makes sense. So we know that our data is fairly accurate. We can make our data much less accurate. Let's put somebody, a 67-year-old in here. Look at what happened to our data. It changed dramatically. Interesting, it made the mean absolutely 25. That I had no idea it was going to do that. But anyway, so our standard deviation went from 4 to 9 years just by pulling that thing up. Let's say we get a 102-year-old. Now we're up to 16 years. Or we could drop this thing back down to 23. So again, now we're saying that this is remember the standard deviation is basically an interpretation of the mean, right? So 23.24 is our mean, but it represents the data pretty well. In fact, it's so well that on average, it's only 3.7 years away from any one person. And that's all we're doing with the standard deviation and the mean. So that's the basics of inferential statistics. At this point, we can calculate every other statistic that's out there. That's all it is playing around with these standard deviations and these means. Right? And all that we're really talking about here is how much do these things, how accurately do they represent, and how much overlap is there, and how little overlap is there, and we're going to talk about that here in a second. All right, here we go. Oh my gosh. Let's apply this thing on a little bit different level. Now you'll notice that there's another statistic up here, z-scores. Right? We'll come back to z-scores here in a second, but it's really straightforward. X minus x bar divided by standard deviation, blah, blah, blah. No worries. Okay? So let's look at standard deviations. Remember our data set originally was 4, and our mean was originally 23.56. So let's just say 23 was our mean. We're just going to make stuff up. So if our mean was 23, right, and our standard deviation was 4, we're just kind of tweaking the data a little bit, but you're going to get the idea. If our data was created from a normal distribution, then here's what we would have. Okay? We would have the mean here at 23. And what we know is there's these things that when you have a normal curve, there's these things called standard deviations. Those are going to match up with that standard deviation that we calculated a minute ago. Right? So 0 standard deviations away from the mean is right at the mean. 1 standard deviation away from the mean is what? You got it. It's 4 more than what the mean was. So if the mean is 23, 1 standard deviation, come on cursor, 1 standard deviation away is 27. 2 standard deviations away from the mean with our data set, okay, would be 31. 3 standard deviations away from the mean would be 35. So we know that 23 was in the middle because that was our mean. That's no standard deviations away because we're right at the mean. So 1 standard deviation away from the mean, we're just going to add what the standard deviation was. It was 4, right? And then another 4, and another 4. And the same thing goes the other direction. So 3 standard deviations below the mean would be 19. 2 standard deviations would be 15. And 3 standard deviations would be 11. The cool thing about this is that assuming that our data was normally distributed, and then we're wanting to apply it to the population, we now know something really cool. We know that 68% of all people, okay, assuming it's normally distributed, fall between -1 and 1 standard deviation. So if you walk out on the street and you just, and let's say our data was great, it was accurate, it represents the population. We walk out of the street and we grab somebody, we have a 68% chance that they're going to be somewhere between 19 and 27 years old. We have a 95% chance that they're going to be between 15 and 31 years old. We have a greater than 99% chance that they're going to be 11 to 35. So 99% of the people, more than 99% of the people, fall between 3 standard deviations. So within those those six bins there. 95% of the people fall between -2 and 2. 68% of the people fall between -1 and 1. These aren't magical numbers. This is just the properties of a normal distribution. We know about this. This is the case of standard deviations. It can change a little bit. The shape of this thing changes a little bit, but it's always the 68, 95, and greater than 99. The other thing that we can do with this is calculate percentile ranks. This is going to be useful for you guys because you use percentile ranks at work, right? So you get, so they're in the 88th percentile, okay, or whatever that is. Well, here's where it comes from. The 50th percentile is right there. 84th percentile. Notice that that's 34 points greater. That kind of matches 68 between those two, so that must mean that 34 happens there and 34 happens there. Exactly right. So we know that that accounts for that 34% of people fall in that one little area right there. Right? So now they're at the 84th percentile. 98th percentile, again, you've got what? You got about 16 there? Or, sorry, that doesn't work. About 14. It's a little over 13, actually. 13.56, I think, is what the real number is. But let's just say 14. Okay. So we know that if you're 2 standard deviations above the mean, you're falling at the 98th percentile. If you're 3 standard deviations above the mean, you're falling at the 99th percentile. In other words, there's less than 1% of the people that can score better than you on that test. Right? Here, 2% of people score better than you. Here, 16% of people score better than you, so you know that 16% of your data falls in this little section out here from 1 to 3 plus standard deviations from the mean. Right? And then again, if you're in the middle, you're in the middle, and we go the other direction. So 16% here, so 84% of people score better than you, right? And here 98% of people score better than you, and so on and so forth. Right? So when you think about intelligence testing, we're putting kids into, with their, do they qualify for services and things like that? It's based on this curve. Okay? So we find out where they fit. Do they achieve a particular criteria? In other words, what's their percentile? Right? And how many standard deviations below the mean are they? Right? And when you have an individual score, this is where this comes in handy. Right? So the individual score, okay, can be calculated using this, right? So the individual standard score. So standard deviations really are just a fancy z-score, right? So a z-score is a standardized score. This is where you take your x, your individual score, and you convert it into something that's been standardized. So let's say we have a standard deviation of 4. So let's play around, or let's say we have a standard deviation of 4 and a mean of 23. So, okay, so our mean is 23, our standard deviation is 4, so keep that in mind. So we're going to look at somebody that had that was 23 years old. So 23 years old minus 23, because that was our mean, divide that by 4. 23 minus 23 is 0. 0 divided by 4 is always 0. So you are at 0 standard deviations away from the mean, and you get how that's working, right? So then we could find what 1 standard deviation is away from the mean. So we would have to, I'm going to kind of reverse calculate that. So let's go 27 divided, or minus 23 is 4. 4 divided by 4 is 1, okay? And you get how that all works. Pretty straightforward. Well, it doesn't have to just be 0, 1, 2, and 3. What happens with somebody that's 22 years old? 22 minus 23, right, is negative 1. Negative 1 divided by 4 is negative 0.25, so you would fall right there. So they would be just below the 50th percentile, negative 0.25. Right? Actually, well, there's 50. Come on, cursor. Negative 0.5, so negative 0.25 would be right in there. Right? So they would be just below the 50th percentile, whatever that is. We can actually go on a table and look that up. Okay? So the z-score of negative 0.25 equals a particular percentile, and believe it or not, that's how it's done. That's how we know how one person that scores at level whatever, he gets a score on an intelligence test, we know exactly what percentile rank they are. This is how we do it, is z-scores. Why do we do these z-scores? It's so you can compare apples to oranges. Example, GRE. The old GRE had like a range of, what was it, 200 to 800, right? That was your total range that you had. The new GRE has got something weird like 125 to 180 or something like that. So you can't really compare those two things together until you convert them into standard scores. In other words, z-scores. And now we can start to look at what percentile rank did you land at. And somebody that took the old GRE versus the new GRE, we can actually compare them because we then know what percentile rank they're at. Whew. That was a load. That was a ton of stuff. We got through it pretty quick. So let's go ahead and move to one last thing. And it's directly related to these curves. It's significance testing. We've talked a little bit about it. I keep hinting at it. We're going to start getting into it here in the future, and this is how we find out if something is statistically significant or not. All right. Let's boil it down into 3 simple things. Actually 4, because one of them isn't on the chart. Right. I've got a series of normal curves on this page, and what I want you to think about is 2 groups. Experimental group, control group. Ultimately, what we want to find out is that group from the same population? Well, wait a minute, they shouldn't be, right? If our hypothesis is that our independent variable has an effect on somebody, will change them in some way or change this group in some way, then ultimately you are not from the same population. Your control group would not then be from the same population as your experimental group, because after they do the intervention, they're changed somehow. They're different people. So we're going to ask the question with significance testing. Well, we'll ask the following question. How much do our curves overlap? That's all we're going to ask. So when we look at these 2 curves, we see there's quite a bit of overlap. And I don't have any numbers up here, and we don't need any numbers. And the lines that are in there represent all the standard deviation stuff, so you get the idea. But with these particular curves, you've got the group A and group B, an experimental group, control group. they're not a lot different. There's quite a bit. There's a lot of overlap between them. We can actually calculate exactly how much overlap, right? And what we're looking for, and just so you know, is basically less than 5% overlap ultimately. And we'll look at why and how that all works down the road. But so these things, they're probably not statistically significant. How about those? Would you say that those two groups are from a completely different population? Heck yeah, right? I'm sure they're from a different population. Look how far apart those means are, the blue lines. Right? Here's where it starts to get a little tricky though. Now we got a little bit of overlap, about 5%. Are those from different populations or not? Well, they could be, but there's a chance that they're not. Right? Here we know they're from different populations. There's no chance that they aren't because there's no overlap at all. Here there's a lot of overlaps. There's a big chance that they're not from the same, or that they are from the same population. Here there's a little chance that they're from the same population. This little overlap is ultimately what we're going to eventually call our p-value. Okay? The probability that we're making a type 1 error. And the amount of overlap that we have means that we are much less likely that there is a significant difference between the groups. So that kind of opens the door to significance testing a little bit. I hope this clarified a few things for you. And of course, as always, hop onto Blackboard or whatever software we are using this quarter and ask questions. Take care. Talk to you soon.